This is the EdExcel AS Level Further Maths Paper 2, covering the FP1 module, and it's from the 2021 series. Question number 1. We have to use algebra to determine the values of x for which x lots of x minus 1 is greater than x minus 1 over x, giving the answer in set notation. We begin with x lots of x minus 1 being greater than x minus 1 over x. And if we rearrange, we would end up with x lots of x minus 1 minus x minus 1 over x being greater than 0. And if we rewrite the left hand side such that we've got a common denominator of x, we end up with x squared lots of x minus 1 subtract x minus 1 divided by x being greater than 0. And recognizing that x minus 1 belongs to both terms, factorizing out the x minus 1, we have x minus 1 multiplied by x squared minus 1 divided by x being greater than 0. X squared minus 1 can be rewritten as a difference of two squares. So we've got x minus 1 lots of x plus 1 lots of x minus 1 divided by x being greater than 0. X minus 1 times x minus 1 is x minus 1 all squared, and then we are multiplying this by x plus 1, and then we divide by x. The result of this is greater than 0. And now, if I multiply through by x squared, we end up with x lots of x minus 1 all squared lots of x plus 1 being greater than 0. We now have to find the range of values of x for which this inequality is satisfied. So we can find out what the critical values are. The critical values, we've got x equals minus 1, 0 and 1. And now if we create a number line, we can test values to find out which range of values we require. Here we have a number line showing our critical values at x equals minus 1, 0 and 1. Now we can test a value which is less than minus 1, such as minus 1.5. And if I substitute that into the left hand side, we've got minus 1.5 multiplied by minus 1.5 minus 1 squared lots of minus 1.5 plus 1. You find we get a positive value. Let's now test a value in between minus 1 and 0, such as minus 0.5. And if I substitute this in, we have minus 0.5 lots of minus 0.5 minus 1 squared lots of minus 0.5 plus 1. We get a negative value. If we test a value in between 0 and 1, such as 0.5, we've got 0.5 lots of 0.5 minus 1 squared lots of 0.5 plus 1, we get a positive value. And if we test a value greater than 1, such as 1.5, then we have 1.5 lots of 1.5 minus 1 squared lots of 1.5 plus 1, we get a positive value. Now we are looking for where the left hand side is greater than 0, and is greater than 0 when x is less than minus 1, when x is in between 0 and 1, and when x is greater than 1. And so if we were to write down our solution in set notation, we have x belonging to a set of real numbers. X is less than minus 1, or x is in between 0 and 1, or x is greater than 1. Here is the solution to the original inequality. Question number 2. The variables x and y satisfy the differential equation d squared y over dx squared plus 15 dy over dx minus 3y squared equals 2x, where y equals 1 at x equals 0, and where y equals 2 at x equals 0.1. We have to use the approximations for the second derivative and the first derivative with h equaling 0.1 to find an estimate for the value of y when x equals 0.3. Essentially what we are finding is, we are finding y3. We are going up in steps of 0.1. We start off with x0 equaling 0, x1 equaling 0.1, x2 then will equal 0.2, and x3 is equal to 0.3. And to find the value of y3, we first need to find the value of y2. We can do that with the approximations and the differential equation shown here. Now, to begin with, we know what x1 is, we know what y1 is, and from this we can find out what dy over dx1 is. So, dy over dx1, using the approximation shown here, that will approximately be equal to y2 minus y0 divided by 2h, and knowing the value of y0, which is 1, and knowing the value of h, which is 0.1, we can therefore conclude that dy over dx1 is approximately equal to y2 minus 1 over 2 times by 0.1, which is 0.2. And similarly, d squared y over dx squared 1 is approximately equal to y2 minus 2y1 plus y0 divided by h squared. We know what y1 is. That's equal to 2. We know what y0 is. That's equal to 1. We know what h is. That's 0.1. And so therefore, we can see then d squared y over dx squared 1 is approximately equal to y2 minus 2 lots of 2 plus 1 divided by 0.1 squared. In other words, d squared y over dx squared 1 is approximately y2 minus 3 over 0.01. What we can now do is substitute those into this differential equation. What we mean by that, we can say then, using the differential equation, d squared y over dx squared 1 plus 15 dy over dx 1 minus 3 y1 squared is equal to 2x1. And substituting this result, and the conditions for y1 at x1, we have the second derivative, y2 minus 3 divided by 0.01 plus 15 lots of y2 minus 1 over 0.2 minus 3 lots of 2 squared equals 2 lots of 0.1. And if we simplify this, we can multiply through by 0.2. And if we do that, well, 0.2 divided by 0.01, that's 20. So we've got 20 lots of y2 minus 3 plus 15 lots of y2 minus 1. And this will approximately equal 2 times by 0.1 times 0.2 plus 3 times by 2 squared times 0.2, which is 2.44. And so if we tidy all of this up, we've got 20 y2 plus another 15 of them. That's equal to 35 y2, and this will approximately equal, well, we've got this 61 over 25, and then we add to that the 60, which comes from 20 times by the 3, and then we add on the 15. So 35y2 is approximately equal to 1936 over 25, and if I divide this by 35, we can therefore conclude that y2 is approximately equal to 1936 over 875. Now that we know what y2 is, we can use exactly the same procedure to find out what y3 is. So if I use the approximation here to find dy over dx 2, then dy over dx 2 is approximately, well, using the approximation shown here, we have y3 minus y1 over 2h, and knowing what y1 is, which is 2, we can therefore conclude over here that dy over dx 2 is approximately equal to y3 minus 2 over 2 times by 0.1, which is 0.2. Now, using the same procedure, finding out what d squared y over dx squared 2 is, you can see then that d squared y over dx squared 2 will approximately equal y3 minus 2 y2 plus y1 divided by h squared. We have just worked out what y2 is, we know what y1 is, we know what h is, and so we can simplify this even further. D squared y over dx squared 2 is approximately equal to y3 minus 2 lots of y2, and we know what y2 is. That's 1936 divided by 875. 75, and then we add on y1, and y1 is, going back to the question, that's 2. So we add on 2, and then we divide this by h squared. 0.1 squared is the same as 0.01. And so if we simplify this even further, you can see d squared y over dx squared 2, that's approximately y3, and then here we've got minus 2 multiplied by 1936 over 875 plus 2, which is minus 2122 over 875. So we've got y3 minus 2122 over 875 divided by 0.01. So now we know what the second derivative is, we know what the first derivative is, and with this, substituting those into the differential equation over here, we can say then that d squared y over dx squared 2 plus 15 dy over dx 2 minus 3 y2 squared to x2. So we've got y3 minus 2122 divided by 875 divided by 0.01 plus 15 lots of y3 minus 2 over 0.2 minus 3 lots of 1936 over 875 squared equals 2 lots of 0.2. We now have a linear equation which we need to solve now. We can multiply through by 0.2, and if we do that, here we would have 20 lots of y3 minus 2122 over 875 plus 15 lots of y3 minus 2. This will equal Well, here we've got 2 times by 0.2 plus 3 lots of 1936 over 875 squared multiplied by 0.2. So we have the result here equaling 3.017283396, and if we simplify, we've got 35 y3 being approximately equal to, well, here we've got this value plus 30 plus 20 times by 2122 over 875, hence 35y3 is approximately 81.52014.054. And if I divide through by 35, y3 is approximately equal to 2.329146873. Here is the approximation for y3. Question number 3. On a particular day, the depth of water in a river estuary at a specific location is modelled by the equation d equals 2 sine of x upon 3 plus 3 cos of x upon 3 plus 6, where x is in between 0 and 7 pi. The depth of water is d meters at time x hours after midnight on that day. For part A, we have to write down the depth of water at midnight according to the model. Well, if x is the number of hours after midnight, that means midnight would correspond to x equaling 0. And so for part A, when x is equal to 0, d is equal to 2 sine of 0 plus 3 cos of 0 plus 6. We've got 3 plus 6, which is 9. And so therefore we can conclude that the depth is 9 meters. For part B, using the substitution t equals tan of x upon 6, we have to show that the equation shown here can be rewritten as d equals 3t squared plus 4t plus 9 over 1 plus t squared. Well, for part B, if t is equal to tan of x upon 6, then the sine of x upon 3 will equal 2t divided by 1 plus t squared cos of x upon 3 is equal to 1 minus t squared over 1 plus t squared, and tan of x upon 3 is equal to 2t divided by 1 minus t squared. And if we replace sine of x upon 3 and cos of x upon 3 with the results shown here and here respectively, then we can say that d is equal to 2 lots of 2t over 1 plus t squared plus 3 lots of 1 minus t squared over 1 plus t squared plus 6. And recognizing that the 6 can be rewritten as 6 times by 1, we've got 2 lots of 2t over 1 plus t squared plus 3 lots of 1 minus t squared over 1 plus t squared plus 6 lots of 1 plus t squared over 1 plus t squared. It's as though these cancel out and simplify to give 1. Now you will recognise we've got a common denominator of 1 plus t squared in every term. So we've got 2 lots of 2t plus 3 lots of 1 minus t squared plus 6 lots of 1 plus t squared divided by 1 plus t squared. And if we attempt to simplify as much as possible, we can conclude that d equals, well, in terms of the t squareds, we've got minus 3t squared plus 6t squared. That will be 3t squared. Then we have, in terms of the t's, 4t. And then we've got 3 times by 1 plus 6 times by 1, which is 9. And then we divide this by 1 plus t squared. And that's exactly the result which we wanted to show. Now, for part C, hence determine, according to the model, the time after midnight when the depth of water is 5 meters for the first time. Give your answer to the nearest minute. So, for part C, we need to set d equal to 5. And if I set d equal to 5, we have 3t squared plus 4t plus 9 over 1 plus t squared equaling 5. And if I multiply through by 1 plus 3 squared, we have 3t squared plus 4t plus 9 equals 5 plus 5 t squared. And so simplifying, we have 2t squared minus 4t minus 4 equals 0. And if we attempt to solve for t will equal 1 plus minus square root 3. And because we want the first time, then we take the positive solution, we take the value of t equals 1 plus square root of 3. And we know what t is, that's tan upon 6. So we have tan of x upon 6 equals 1 plus square root 3. So x upon 6, that will equal the inverse tangent of 1 plus square root 3, which is 1.219, etc. And so if we solve for x by multiplying through by 6, we've got 7.319, etc. And so therefore, for the time, we've got 7 hours, and then to find out how many minutes we've got, that's 19 minutes. So the time is 7:19 AM. Question number 4. With respect to a fixed origin O, the points A, B and C have position vectors given by OA equals 18i minus 14j minus 2k, OB is equal to minus 7i minus 5j plus 3k, and OC is equal to minus 2i minus 9j minus 6k. The points O, A, B and C form the vertices of a tetrahedron. For part A, we have to show that the area of the triangular face ABC of the tetrahedron is 108 to 3 significant figures. Now, let's first of all draw a sketch of the tetrahedron. Here is a tetrahedron. The area of this tetrahedron is given by 1/2 times the modulus of the cross product between AB and AC. Now, let's begin by finding the vector AB and AC. So, the vector AB is equal to the vector OB minus OA. Vector OB, we've got minus 7i minus 5j plus 3k minus 18i minus 14j minus 2k, and it turns out the vector AB is equal to minus 25 I plus 9j plus 5k. And if we work out the vector AC, that's equal to OC minus OA. So this is equal to minus 2i minus 9j minus 6k minus 18i minus 14j minus 2k. So it turns out we would get minus 20i plus 5j minus 4k. And so therefore we can now find the cross product between AB and AC. So AB cross AC, we've got AB, which is minus 25i 9j plus 5k. AC is minus 20i plus 5j minus 4k. Now, we can use our calculator to work all of this out. So if we were to use our calculator, let's go to the vector submenu, define the first vector. We have minus 25, 9 and 5. Define the next vector, minus 20, 5 and minus 4, and then we can multiply those vectors together, and if we do that we end up with minus 61i minus 200j plus 55k. And so therefore, for us to find the area will equal 1/2 times the modulus of minus 61i minus 200j plus 55k. So we've got 1/2 multiplied by, well, if I work out what the modulus of that is, we have the absolute value of this vector. So we've got 1/2 times by 216.208, etc. So if I times this by 0.5, we get 108 units squared to 3 significant figures. Now for the next part of the question, we have to find the volume of the tetrahedron. Now the volume that will equal 1/6 lots of the modulus of AO dot product with the cross product of AB cross AC. We need to work out what the vector AO is. For part B, the vector AO is equal to the vector minus OA. So we have minus the vector OA. So we've got minus, and then in brackets 18i minus 14j minus 2k, which is minus 18i plus 14j plus 2k. And knowing what the vector AO is, we can now find out the volume. The volume we have 1/6 lots of the modulus of, well, here we have the vector AO, and then we dot product this with the vector AB cross AC, which is this over here. So if we work this out, we've got 1/6 times the modulus of, well, here we've got minus 18 times minus 61, 14 times by minus 200, plus 2 times by 55, so we've got 1/6 lots of the mod of minus 1592. So the exact volume will equal 796 over 3 units cubed. And now for part C, the oak wood block is made in the shape of the tetrahedron with centimeters taken for the units. The density of oak is 0.85 grams per centimeters cubed. We have to determine the mass of the block, giving an answer in kilograms. So, for part C, we've got the mass, which equals the density multiplied by the volume. Now the density is given by 0.85 grams per centimeters cubed. And what we can do is convert that into kilograms per centimeters cubed by dividing that by 1000. So we've got 0.85 divided by 1000 multiplied by 796 over 3, which is the volume, which we worked out over here. And if we work out what this is, we've got 0.85 over 1000 times 796 over 3. So it turns out the mass is equal to 0.2255, etc., which to 3 significant figures, we've got 0.226 kilograms to 3 significant figures. Question number 5. The point P with coordinates AP squared to AP, where A is a positive constant, lies on the parabola with equation y squared equals 4ax. The normal to the parabola at P meets the parabola again at the point Q with coordinates aq squared 2aq. For part A, we have to show that q equals minus p squared minus 2 over p. Here is a diagram of the situation. We've got our parabola, the equation of the tangent at the point P, and the equation of the normal at the point P. And this normal intersects the parabola once again at the point Q. Now, we have to express Q in terms of P. For this, we can find out the equation of the tangent and the normal. So, if we differentiate implicitly, beginning with y squared equals 4ax, we can therefore conclude that 2y lots of dy over dx is equal to 4a, from which we can see that dy over dx is equal to 2a over y. And at the point P, with coordinates ap squared 2ap, we can find out the value of dy over dx. So we have 2a divided by the y coordinate, which is 2ap, and so it turns out here dy over dx is equal to 1 over p. So this 1 over p would represent the gradient of the tangent. And so we can conclude from this that the gradient of the normal will be given by minus p. So the equation of the tangent then, that will be y minus 2ap equals 1 over p lots of x minus ap squared. The result we see here is the equation of the tangent, and the equation of the normal, that will be given by y minus 2aq equals minus p lots of x minus ap squared. So what we have here is the equation of the normal. And knowing the equation of the normal, we know that the normal intersects the parabola once again at the point Q. So at the point Q with coordinates aq squared 2aq, we have y, which is 2aq, and then we subtract over here, this is p. We subtract 2ap, and this is equal to minus p lots of a q squared minus a p squared. And if we expand out and simplify and rearrange, you will find we have pq squared plus 2q minus 2p minus p cubed equals 0. Of course, we've divided through by a. And because we know that q equals p, and that's just by inspection by looking at the coordinates, we can see then q minus p will be a factor of this. And if q minus p is a factor, then inside the bracket, here we would have pq, because q times by pq gives pq squared, and minus p times by pq that will give minus p squared q, but then we can add on a p squared and then a 2 to balance out the terms. So q times by pq squared gives pq squared, then we've got 2 times by p squared, and that will give qp squared, and then we've got 2 times by q, that's 2q, and we've got minus p squared q, and then we've got minus p cubed minus 2p. So either q minus p equals 0, or we've got pq plus p squared plus 2 equals 0, from which we can see p is equal to q, or we have, solving this, pq equaling minus p squared minus 2. And from this we can conclude that q is equal to minus p squared minus 2 over p. So that's what q is, and that's exactly what we wanted to show. We'll call this equation 1 for now. And now for part B, hence show that pq squared equals ka squared over p to the 4 lots of p squared plus 1 to the power of n, where k and n are integers to be determined. Now to do this, we would require the use of Pythagoras. So if we were to use Pythagoras, we can form a right-angled triangle, such as the one we see here, and the distance from P to Q in terms of the y's, that will be 2AP minus 2AQ, and the difference in terms of the x's will be given by AP squared minus AQ squared. And we are finding PQ all squared. So we can now use Pythagoras for part B. So PQ squared, that will equal from Pythagoras, well, we have AP squared minus AQ squared, which is all squared, and then we have 2AP minus 2AQ all squared. So now we need to tidy all of this up to somehow get a result which is in the form over here. So if I factorize out the a from this bracket and then I need to square it as well, what we have is inside a larger bracket a, and then p squared minus q squared, close big bracket, that's all squared. And then here, if I factorize out a to a, then here I have p minus q, close big bracket, and this is all squared. So using the laws of indices, we have a squared, lots of p squared minus q squared squared, plus 2a all squared, lots of p minus q squared. And recognizing that the bracket over here can be written as a difference of two squares, we have a squared, lots of p minus q, lots of p plus q squared, plus 4a squared, lots of p minus q all squared. And again, using the laws of indices, we have a squared, and then here we've got p minus q squared, lots of p plus q squared, plus 4a squared, lots of p minus q squared. And if I take out an a squared as a common factor, and then if I also take out a p minus q all squared as a common factor, then inside this bracket I will end up with p plus q all squared plus 4. Let's call this equation 2. And I can replace the q over here with minus p squared minus 2 over p. So if we substitute in equation 1 into equation 2, then pq squared will equal a squared, lots of p minus, well here we'd have minus p squared minus 2 over p all squared. And then if I open up a bigger bracket over here, we have p plus q, so that's p plus minus p squared minus 2 over p all squared plus the 4. So if we tidy all of this up, the a squared is still factored outside, and then if we rewrite this bracket such that we've got a denominator of p, and recognizing that the minus and the minus would give a plus, we end up with p squared plus p squared plus 2 divided by p all squared, and then inside this bracket we have p squared minus p squared minus 2 over p squared plus 4. So, tidying this up even further, we have a squared, lots of 2p squared plus 2 divided by p squared, and then inside this bracket we have minus 2 over p squared plus the 4. So we've got a squared. Now here, this bracket we can split up and simplify. We've got 2p squared divided by p. That's the same as 2p. And here we've got 2 over p squared. And then here we've got 4 over p squared plus 4. So if we tidy this up even further, we've got a squared, and then here, this bracket can be simplified even further. We've got 2 lots of p plus 1 over p squared multiplied by 4 lots of 1 over p squared plus 1. So, using the laws of indices, we've got a squared, lots of 2 squared, lots of 4, lots of p plus 1 over p squared, lots of 1 over p squared plus 1. And so now we need to simplify all of this. 4 times by 4 is 16, multiplied by a squared. That's 16a squared. And then p plus 1 over p we can combine. That's the same as p squared plus 1 over p all squared. And then this we can simplify to 1 plus p squared over p squared. And so we've got 16a squared, and over here this is the same as p squared plus 1 squared divided by p squared, and then here 1 plus p squared is the same as p squared plus 1, and I'm dividing this by p squared, and so combining I've got 16a squared divided by p squared times p squared, which is p to the power of 4, and then in this bracket we've got p squared plus 1, which is squared, and then being multiplied by p squared plus 1, so that's the same as p squared plus 1 all cubed. And so what we see here is a result of pq all squared, from which we can conclude k is equal to 16, n is equal to 3.